Hello everyone, welcome back to Diksha Karnataka YouTube channel, and you are watching your favorite series Sankalp KCET 2026, and today is the time for ray optics and optical instrument part 2. Here we are going to discuss about refraction and Snell's law. In our previous part we have discussed about reflection, and today we are going to discuss about refraction, and then in our next third part we will discuss about lenses, and fourth part will be based on the optical instrument, right? Now before I continue, first of all, as I always say, please join our WhatsApp channel. The link is given in the description. All the lecture notes, important announcement, everything will happen through our WhatsApp channel, so don't forget to join our WhatsApp channel immediately right now. Before you proceed with the video, first join our WhatsApp channel, then you can continue this video. Also, if you have not yet subscribed, then don't forget to subscribe to our channel as well. Now let's see why I am saying this, because as you can see, here is our result from last year. These students followed our WhatsApp channel, joined our WhatsApp channel. They also subscribed to our YouTube channel, and see their result. They have followed us from the beginning, and at the end of the year their result is here, and many more students are here as well. And it can be you next year if you do whatever I am saying it to you, because they followed it, they get the result. So if you are following it, you should also get the same result as them, right? So now let's look into the chapter summary. I have already discussed it in our last video as well. Reflection, laws of reflection, spherical mirrors, sign convention, mirror equation and magnification we have discussed in our part 1. Today I am going to discuss refraction, laws of reflection and Snell's law, refractive index, total internal reflection and application of total internal reflection. These we will discuss in today's lecture. In next lecture we will discuss lens and prism, refraction at spherical surface, refraction by a lens, lens equation, refraction through a prism. Everything we will discuss in our third lecture, and in our fourth lecture we will discuss optical instruments, microscope and telescope, right? Now let's continue with the lecture. So first let us understand what is refraction. Here we have a ray of light which is falling between a medium, separating a medium which is separating this original media and the second media. So this is falling in the separating plane. Once it falls into this point, part of the light will be reflected back, and part of the light will go into the second new medium. Okay, so for example, light is falling on a water. Okay, pond, it can be a pond, it can be a lake, it can be a glass of water. Okay, when light falls on that glass, okay, part of the light reflects back to the first medium, that is air. Part of the light goes into the second medium, which can be whatever water we are talking about, say glass of water. So if you shine a torch on a glass of water, part of the light will go into the medium and part of the light will reflect back. Okay, so reflection and refraction is happening, and obviously some part will be absorbed by the medium as well, but we will not talk about absorption in this lecture. The incident ray, refracted ray and the normal to the interface at the point of incidence all lie on the same plane. So this is similar to that of the second law of reflection, right? The incident ray, the refracted ray and the normal drawn on the point of incidence, they all lie on the same plane. So basically they all, you can see there is a plane shown over here. So they all lie on the same plane. Okay, so they all lie on the same plane, similar to that of the second law of reflection, but the here this comes first, because the second law of reflection is very important. It is also called Snell's law. It states that the ratio of sine of the angle of incidence to the sine of the angle of refraction is constant. Remember that the angle of incidence I and refraction R are the angles that the incident and refracted ray make with the normal respectively. So here if you see that here we have a incident ray and we have a refracted ray. The incident ray makes an angle I with the normal, and the refracted ray makes an angle R with the normal, right? This light is falling, this is refracted ray, so we are only considering refraction. So according to Snell's law, it says that sin I by sin R is a constant. Okay, sin I by sin R is a constant. It does not matter what is the meaning of that. Suppose you change the angle of incidence. If you change the angle of incidence, the angle of refraction will also change, right? If you say a new angle, say I dash, and the angle of refraction, say R dash. So if you change the angle of incidence and angle of refraction, okay, the angle of incidence, if you change the angle of incidence, angle of refraction will change as well. But no matter whatever is the value of I, no matter whatever value of the value of R, sin I by sin R will always remain constant. Okay, sin I by sin R will always remain constant for a particular pair of medium, obviously. For a given pair of medium, okay, it should have been mentioned over here as well. For a given pair of medium, for a given pair of media. Okay, why media? Because medium is singular, media is plural. Okay, for a given pair of media, the ratio of sine of the angle of incidence to the sine of angle of refraction is constant. Okay, now let's dive into detail about that constant. Okay, here N21 is called the refractive index of the second medium with respect to the first medium. So if you remember, here we had light falling. Okay, now let me simplify, draw this diagram with a simplified attitude. So now see, this is a I, this is R, and what we said, sin I by sin R is constant. So this is, say, first medium, and this will be the second medium. Okay, so we are always interested in the refractive index of the second medium. Okay, and we say this medium has a refractive index of N21. Okay, we will go back and we will see what is the refractive index of the first medium, but for now we are only interested in the refractive index of second medium. So here N21 represents the refractive index of the second medium with respect to the first medium. If N21 is greater than 1, so that means after calculating this ratio, if you find that this ratio value is greater than 1, that is R value is less than I. So if the refractive angle is less than that of the incident angle, the refracted ray bends towards the normal. So it bends towards the normal, more towards the normal. If N21 is greater than, so this case N21 is greater than 1. Okay, that is the refracted ray bend towards the normal. In such case, medium 2 is said to be optically denser. So this means this medium will be optically denser. So for example, water and air. When light enters from air to water, okay, the light bends towards the normal and the refractive index of water is more. Okay, the refractive index of water is more. So this is called refractive index. Sometimes in short we will also say refractive index as R dot I. Okay, R dot I nothing is refractive index. This is a short form acronym, right? So this is called optically denser medium. In the other hand, if N21 is less than 1, then R is greater than I, right? If it is greater than 1, so suppose this case, what will happen? Now you see that, so initially this was I, now if it is less than 1, then it will be, here N21 is less than 1. Okay. This is the case where incident ray in a denser medium refracts into a rarer medium. So it is called optically rarer medium. For example, if you just reverse the scenario. So for example, in the first case we said that light is traveling from air to water. Now if you take the same example, now light is traveling from water to air. Okay, when light is traveling from water to air, the light ray bends away from the normal because air is optically rarer than water. The other term, the opposite to optically denser, is optically rarer. Okay, optically rarer. Optical density should not be confused with mass density. Okay, which mass density is mass per unit volume. Optical density is solely based on the refractive index of the medium, relative refractive index of the medium. Okay, it is possible that mass density of an optically denser medium may be less than that of an optically rarer medium. Okay, optical density is the ratio of speed of light of in the two media. We'll come to that. Okay, for example, turpentine and water. Mass density of turpentine is less than that of the water, but its optical density is higher. That means if you measure the density, normally water has a density of 1. Okay, density of water is 1. Density of turpentine is about 0.9. Okay, 9 something. But if you see that the density of turpentine is much lesser than that of the water. That means if you add turpentine into water, turpentine will be floating on water. Now what is turpentine, by the way? Turpentine is a liquid which is used in paints. If you have smelled a very pungent smell after your room or your classroom is newly painted, that smell is basically coming from the liquid called turpentine. Turpentine is a primary solvent for paints. Okay, it is used in paints to dissolve the paint. Okay, for if the paint is very dense, they add turpentine to it to make it a little bit thinner. Okay. Now turpentine, so turpentine is turpentine is mass density wise rarer to that of water, right? That means turpentine is lighter. But when you consider the refractive index of turpentine is slightly higher than that of water. Water is 1.33, turpentine is slightly more than that of water. Okay, 1.35 or 1.4 approximately. Okay, now refractive index can be when light travels from a rarer medium when light travels from one medium to another, there are two incidents that happens. One is, suppose you are observing a liquid from top. Okay, you are at air, this is air. Okay, this is say air and this is say water. Okay, now if you observe this, suppose this is a fish tank. Okay, aquarium. Okay, there are a lot of some fishes are flying inside it. So you are trying to measure its depth from looking into it. So you can either look into it like this, okay, or you can look at some angle. Okay, you can either look at some angle or you can look at some right angle. Okay, this is normal view, this is an angular view. Now no matter from where you are looking, okay, the height, the depth of the fluid will not be the actual depth that you are expecting. You will measure a depth which is much smaller than the original depth. You will observe a depth which is much smaller than the original depth. Okay, this is called apparent depth. Okay, now this can be calculated using geometry. We will do that in later part where we'll solve some numericals, but right now we are not doing that. But you have to understand that when you are observing, suppose this is a fish tank, you are observing like this inside the water, then you will see that the floor of the aquarium or the fish tank, it will come to be raised. It is called raised. Okay, because of the apparent depth, the bottom of the aquarium will be slightly elevated than actually it is. This is called apparent depth. Now based on the fluid, okay, based on the liquid, the apparent depth can vary. Okay, and there is one more thing. When light travels through a parallel when light passes through a parallel glass plate, okay, where the edges are parallel to each other, okay, it is called glass slab. You may have done this experiment in your laboratory. If you have not done, then you will do that. So here when light enters through one surface, it exits through the other surface. Okay, this happens only when the edges are parallel. You have to remember that this happens only when the edges are parallel to each other, and after the light emerges, it does not deviate. It does not deviate angularly. Angular deviation will be 0. We have discussed about angular deviation in our last class, if you remember. So angular deviation in this case will be 0, but what it will do, it will laterally shift. Okay, it will shift laterally. So original path was this one, the new path is this one, that is they are parallel. So if you see that this ray and these two rays are parallel, the original ray and the emergent ray, they are parallel, but they are not in the same line. They have shifted by a small amount. This shift is called a lateral shift. This shift is called lateral shift. Okay, you have to do that, and from this measurement even you can calculate the refractive index of this medium as well. Okay, now let's see one question. Consider a glass slab which is silvered at one side and the other side is transparent. Given the refractive index of the glass slab to be 1.5, if a ray of light is incident at an angle of 45 degrees on the transparent side, the deviation of the ray of light from its initial path when it comes out of the slab is. Now let us understand this question. It is similar to that case we have seen. So here we have suppose glass slab, this side is silvered. Silvered means this side is basically acting as a mirror. So it is a question combination of mirror and reflection. So one light incident like this, and it gets refracted, and then once it falls on this surface, it gets reflected, right, and again it gets refracted. This angle is given as 45 degrees. Okay, and they said what is the deviation, what is the angle of deviation. Angle of deviation, as we said, this is the angle of deviation, this angle is angle of deviation delta. Okay, original path and the final path. Okay, so this is the angle of deviation. Now how to calculate the angle between original path and final path is called the angle of deviation. So if you are wondering, if you missed my yesterday's lecture, day before yesterday's lecture, so this angle is delta. Okay, now how to calculate this angle. So here it is a very simple logic. Okay, because this angle is 45 degree, you can consider, because the apparent depth, the height will rise to some point, and if you consider this as the position of the mirror, this as the position of the mirror, then you will see that if this angle is 45 degree, this angle will also be 45 degrees, and this angle will also be 45 degrees. This is parallel rays, parallel lines. So if they intersect, this angle will be equals to this angle, right? So this angle 45 means this angle will also be 45. This is parallel to normal, right? Similarly, this angle will also be 45, angle of reflection. This angle will also be 45. So basically what you need to consider, simple old formula that we used in our previous lecture, same formula, that is delta equals to 180 degrees minus 2i. It is independent of this refracting medium. Does not depend on the refraction. So angle of deviation, if there is a reflection happening, then you can always use this formula to calculate the angular deviation. So 180 degrees minus 2 into 45, that is 180 degrees minus 90, that is 90 degrees. The problems in KCET are not mathematically super difficult, Okay, logically it can be. If you understand the logic, then you can solve such questions in ease. Okay, the formula is simple, the calculation is simple. You don't need to calculate the angle of refraction, then again what is the angle of incidence over here. Those parts are not required. This is a very simple problem, so try to keep it simple, that you can consider this to be a virtual reflection method. Only the plane is not this, plane will be somewhere here. That's it. The angle of incidence will be 45. This is also 45. So angle of deviation will be 180 degree minus 2i. So this is the simple logic. If you apply it, you can solve such questions easily. Refractive index is dependent on the wavelength of light. So n basically dependent on the wavelength of light, and it is inversely proportional to wavelength of light. Okay, so basically higher the wavelength, lower is the refractive index. So can you tell me which one has a higher wavelength? From Vib gear, right? You know that, right? VIB GYOR, Vib gear or Vib gear. Okay, so violet has the smallest wavelength. Violet in the visible region, of course. So this has the smallest wavelength, and this has the largest. Okay, smallest and largest. Everything is in between, in this limit, in this order. So indigo is after violet, blue is after indigo, green is after blue, and yellow is after green, orange is after yellow, and red is the highest. Okay, so all this is the order. If you remember Hibgier, then it will help you to remember the order as well. Mostly you have to remember violet and red. Okay, because most of the questions will be asked based on violet and red only. Okay, they generally will not ask you orange and red or violet and indigo. Generally they do not ask, but in case they ask you, you have an idea that okay, this is the order, this is how we can answer. Also you have to understand yellow falls between these two, exactly, almost average. Okay, so if you find the wavelength, approximately this is 700 angstrom, 700 nanometer, and this is 400 nanometer approximately, and it will be yellow is 550 nanometer approximately. This is approximated value. Okay, now also the refractive index is dependent on the speed of light in the medium. So it depends on the wavelength, it depends on the speed of light as well. And as we know that as the different colors have different speed in a medium, right? So the absolute refractive index is given by n equals to C by V. What is the meaning of absolute refractive index? Absolute refractive index is when the first medium is free or vacuum. Okay, if the first medium is vacuum or free, then that is called absolute refractive index. Okay, so if the first medium is vacuum, that is light is falling from a free space to a medium, then you can consider that to be absolute refractive index. For all practical purposes, air, you can consider the first medium to be air as well. Okay, because air is very less, in terms of refractive index it is 1.02, which can be approximated to be 1. Refractive index of vacuum is 1. Refractive index of vacuum is 1. Refractive index of air is also approximately 1. Okay, for any other medium, refractive index is given by C by V. C is speed of light in free space, speed of light in vacuum, and v is the speed of light in that particular medium. So even without doing any experiment, you just measure the speed of light in a particular medium, you can calculate its absolute refractive index. If nothing is mentioned, then that refractive index generally represents absolute refractive index only. So for example, if I say the refractive index of glass is 1.5, okay, refractive index of flint glass is 1.5, refractive index of crown glass is 1.6, that means they basically represents the absolute refractive index. And relative refractive index is given by N21 is given by V2 by V1. Okay, so if you are measuring the refractive index of the medium 2 with respect to medium 1, first it will be sorry, there is one mistake, it will be V1 by V2. Refractive speed of light in the first medium, from where the light is coming and where the light is going, V1 by V2. Okay, speed of light in the and in 1 2, so this is how we compare the speed of light in the different mediums. I told you there is a relationship. So N21 is the speed of light in the refractive index of the second medium with respect to the first medium, and here N12 is the speed of light in the second medium divided by speed of light in the first medium, and it is equals to 1 by N21. Right? So if the refractive index of water is given 1.33, what is refractive index of air? If the refractive index of water is 1.33, then refractive index of air will be 3 by 4. Okay, with respect to water. You think about this question. Refractive index of water is 1.33. What is refractive index of air with respect to water? Okay, think about this question. I already told you the answer, and mention it in the comment below. I will check, and if you have any doubts, I will also clear that. Now let's move into the next concept, which is total internal reflection. Now before going into that, let us understand the concept. Suppose we have a medium. Okay, light is traveling from a denser medium, okay, to a rarer medium. That means light is traveling from, say, water to air. Very important. Light is traveling from water to air. So this is denser medium, this is rarer medium. When light falls at some angle, so you have a torch over here. You have lit up a torch, LED torch at the bottom of a water tank, and you are observing what is happening. Okay, so when the light is falling here, what will happen? This is a denser medium, this is a rarer medium, so this is the angle of incidence. So angle of refraction will be more, right? Because the relative refractive index is less than 1, so it will move away from the normal, right? So R is greater than I. Now if you increase the value of I by a small amount, what will happen? The refractive angle of refraction will also increase, right? Sin I by sin R has to be constant, and at certain angle of incidence, okay, the light ray will no longer pass into the first medium, but it will pass through the plane which divides these two medium. This is a very special angle. This angle is a very special angle. This is called critical angle and denoted by theta c, or sometimes IC. Okay, so this is the critical angle. This angle is called critical . This This is a very natural thing. So if you are increasing the angle of incidence, the angle of refraction keep on increasing until at some angle of incidence the light ray no longer goes to the first medium, it travels through the medium which is separating these two media. Right? Now what will happen if you keep on increasing the angle, and if you increase the angle even further? If you increase the angle even further, instead of going into the first medium, it will now reflect back according to the law of reflection, and the entire 100% light will come back to the first medium itself. 100% of the light will come back to the first medium itself. This phenomena is called total internal reflection. When light travels from an optically denser medium to a rarer medium at the interface for the certain angle of incidence, the refracted ray light passes exactly between the planes separating the two medium. Okay, two media, it will be two media. So it passes through exactly between the planes separating the two media. This angle is called, in this case the angle of refraction is 90 degrees. Obviously, what is the angle of refraction in this case? Angle of refraction in this case is 90 degrees, right? Now this angle of incidence is called critical angle. We already discussed that. Now from Snell's law, now let us try to find the critical angle. Okay, from Snell's law, sin I by sin R equals to refractive index, right? So sin I by sin 90, what was sin I, if you remember? So that case we will only draw that critical angle case now, we will not draw any other case. So this was our angle of incidence and this was our angle of refraction. So this is 90 degrees, so this is theta c. Okay, so in this particular case, so let me write this as theta c. Now this refractive index of this medium into 1, this is medium 1, this is medium 2. Okay, refractive index of the rarer medium is basically given by Snell's law, sin I by sin R. Now sin 90 value is 1, so from there we can see that sin theta c is n to 1, or but here you have to remember that the first medium is denser, second medium is rarer. First medium is denser, second medium is rarer. So if you calculate this value, this will be less than 1. This value will be less than 1. But if you want to find the refractive index of the denser medium, that is water, in that case what you have to do, you have to take the reciprocal of it. We have already shown you that n12 will be 1 by n21, that is 1 by sin theta c. So this is the formula for now critical angles generally calculated like this: sin theta c is 1 by n12, because most of the cases n12 only will be given. Refractive index of water is 1.33, that will be given to you. So from there theta c generally calculated using this value 1 by n12. Okay, this is the formula to calculate critical angle, and from critical angle calculating refractive index, this is the formula. Okay. When the angle of incidence is greater than the critical angle, incident light, instead of refracting to the second medium, reflects back to the first medium. This is called total internal reflection. This phenomena is called total internal reflection. Now as I said, this is a 100% reflection. Now you can see the refractive index of some known material and their corresponding critical angle is given. For example, water, the example I was giving to you. So water has a refractive index 1.33 and its critical angle is approximately 49. For crown glass it is 1.52 and refractive index is 41. Dense flint glass it's 1.62 and critical angle is 37, and diamond having one of the highest refractive index 2.42 and its critical angle is very small, 24.41. This is one of the reason that if you see a real diamond, it glitters, especially it's called brilliance of a diamond. Okay, diamond has a very special glittering which is called brilliance of a diamond, and that happens because of the small critical angle. Uncut diamond is as dull as any other stone. Okay, but when you cut the diamond in particular angles, so that light can enter into the diamond through all possible sides, but it can exit particularly through only one side. That is why the diamond looks so beautiful. Okay, it depends on the cutting of the diamond. The looks of a diamond depends on the cutting of a diamond, and the artist usually figure it out in the past that if you cut a diamond in a particular direction, it gives you a brilliant color, brilliant look, and that's why diamonds are expensive. And one more reason is that its refractive its critical angle is very small, so light can enter, and once it is inside the diamond, it keep on reflecting total internal reflection, and then it can come out through only one particular direction. So light comes through all sides but exits through only one particular side, and you see a very large amount of light coming through it. That's why the diamond appears to be that brilliant. Okay, let's see one question. For a given pair of transparent media, the critical angle for which color is maximum? So critical angle for which color is maximum? Now first we have to understand what is critical angle. Critical angle sin theta c is basically 1 by n to 1. Always use this formula. Okay, not n to 1, n 1 to. Always use this formula because this is greater than 1, n 1 2 is greater than 1, right? Generally first medium you can consider to be vacuum. So if you consider first medium to be vacuum, then it will be simply 1 by n. Okay, if light is, suppose this medium is water and this is say vacuum, then the absolute refractive index of this medium is n, right? So whatever light is happening, you can use this formula, right? Now what we know that refractive index is inversely proportional to the wavelength lambda. Refractive index is inversely proportional to wavelength lambda. That means sin theta c is directly proportional to lambda. Why? Because enemy of enemy is my friend. So inverse of inverse is straight, right? Division of division is multiplication. So enemy of enemy is my friend. So from that logic, sin theta c is proportional to lambda, or you can say that theta c is proportional to lambda. Sin theta is simple formula, right? So theta c is proportional to lambda. Higher the wavelength, higher is the critical angle. So who has the highest wavelength? Okay, red has the highest wavelength, so that means critical angle for red will be maximum, critical angle for red will be maximum, and critical angle for violet will be minimum. Now here is an application of total internal reflection. Here mostly some prisms are used as changing the direction of light coming through particular direction, and they have a lot of applications. For example, one mechanism, this mechanism is used in a prism periscope. Okay, and that prism periscope is used in underground bunkers, from where the soldiers can look into what is happening in the field. Also in the submarines, they observe whatever is happening on the surface of the water through that periscope, right? So this is one of the application of total internal reflection. As you can see that light travels through this, and once it falls on this surface, it is particularly cut in such a way that this angle of incidence is greater than critical angle, so it deflects back, and you observe the image over here, and this one you can see, right? Here it is an inverter. Okay, this also used in some projectors, some cameras, right? So light travels like this, and once it comes out of the prism, it is 100% inverted. Okay, this is another inverter, but in this case inversion happens on the other side of the prism. In this case the inversion happens on the same side of the prism, right? So here is the object, and after it gets refracted, you get an inverted image. Okay, this is the direction changer. Both of them are inverter. One is inverting in the same direction of the object. Here it is inversion happening in the other side of the object. Optical fibers are extensively used for transmitting audio and video signals through long distances. So if you are watching this video using an Wi-Fi, there is a 99% chance that you have an optical fiber connection in your home. It can be Jio, it can be Airtel, it can be any other fiber net company. So if you have heard the term fiber net, okay, that is basically where optical fibers are used to transmit data. So when the video is transmitted to you through some YouTube server, the server is sending that data to the optical fibers, and that optical fiber is transmitting the data to your home through some technology. Okay, there are in between some technologies involved. If you want to become a communication expert in future, then you will learn about optical fiber technology as well. Okay, so optical fibers are extensively used for transmitting data. Okay, optical fibers too make use of the phenomenon of total internal reflection. Optical fibers are fabricated with high quality composite glass or quartz. Quartz is a crystal, mostly it is a glass, high quality glass. Each fiber consists of a core and a cladding. Okay, core is the center, cladding is the outer cover. Okay, each fiber consists of a core and a cladding. The refractive index of the material of the core is higher than that of the cladding. Okay, so refractive index of the core is higher and cladding is lower. So basically what happens is that inside an optical fiber, the small portion is a very thin wire. Okay, if you have seen the optical fiber when the person came into your house to install the fiber optics, or if you may have seen into some exhibition, there used to be some lights. When we are kids, those lights were very popular. Okay, the light, nothing is there, but at the top of the fibers you can see some glowing light. Okay, that was one of the popular exhibit at when I was a student. I was even younger than you, most of you, when I was in schools. Okay, say 7-8 class, that time those optical fiber lights were very popular. Okay. Optical fiber technology in the communication was still under development back then. Okay, but it developed very quickly, and nowadays it is in use everywhere. Okay, starting from your mobile phone technology. If you are calling someone, how the information is getting traveled from you to the receiver, mostly it is happening that when you are calling it, your signal is transmitted to the nearest tower. From that tower it is transmitted through some optical fiber technology to the receiver ends tower, and from there it is again transmitted through the air. That's how the air to surface communication happens. Also there is one more very important part is Pacific cable. Okay, trans-Pacific fiber cable, fiber optic cable, which is laid under the ocean. Okay, under the ocean there is a very huge communication cables are laid, and it is connecting the entire world. Okay, it is connecting with India, with USA, UK, Russia, Germany. All the countries are basically interconnected through that hidden cables. Okay, most of the cables are laid under the ground, except when it is coming to your house. Most of the cables are under the ground, and you don't generally see them, right? So optical fiber technology is the most important application of total internal reflection. So when the light enters into this, the light is traveling from a denser medium to a rarer medium. Okay, and the refractive index is not simple. Okay, it is basically changing with each and every passing medium, and once it reaches to the end, it basically totally internally reflected, and they travel like this. Okay, this is not the exact diagram. I have taken this from your book. Exact diagram is slightly different. Anyway, that will be I will leave that discussion for some another day. Okay, but if you are interested in optical fiber technology, you can go and do some research on your own and find out how the data or information is getting traveled from one country to another or one place to another, right? Now each fiber consists of a core and a cladding. The refractive index of the material of the core is higher than that of the cladding, and that's why total internal reflection happens and information travels from one end to another without very less absorption. Now another beauty of this optical fiber is that they do not generally absorb the information, so it can travel kilometers of kilometers without getting without reducing the energy. Okay, it is very important. Okay, if the energy, the information that you want to send, if the entire energy is getting absorbed by the medium, then at the end point you will not get any information. Okay, so there are some boosters that you have to use, but that number of boosters or frequency of the boosters is very less because the energy that is absorbed inside the optical fiber is very less, so you can install that booster after few kilometers. Okay, it is not like 100 meters, every 100 meters you have to install a optical fiber cable. If epsilon naught and mu naught are the permittivity and permeability of free space, and mu and epsilon are the corresponding quantities for a medium, then refractive index of the medium is. Now this is slightly higher level question, higher level question in the sense that the concepts involved in this are not yet taught in your I have not taught you, but there is a formula that you need to know. In electromagnetic wave chapter we will discuss about that formula. That formula is speed of light is basically given by 1 by epsilon naught mu naught, square root of epsilon naught mu naught. This is speed of light in vacuum. Speed of light in any other medium is given by 1 by square root of epsilon mu. Okay, epsilon mu, no naught. Naughts are only for vacuum or free space, so that's why speed of light in vacuum is this. Speed of light in any other medium is 1 by epsilon mu. So what is the refractive index of the medium? Refractive index of the medium is V by C, sorry, C by V, C by V. So C is 1 upon mu naught epsilon naught, and this is 1 by 1 upon, so it will go up, mu epsilon, so you will get this as mu epsilon divided by mu naught epsilon. Okay, mu epsilon by mu naught epsilon naught, so option A is correct in this case. Okay. So this is actually this is an easy question, but once you are familiar with this formula, once you have practiced this formula 1 to 2 times, then this is a very easy question. Okay, now this is a homework question. Now every time I say that homeworks are very important. Okay, even small practice can make you ready for your future, so always try to answer the homework question and answer them in the comment below. This, pause the video if you want and answer the question. This is easy question, so pause the video, answer the question immediately into the comment. Now this is the second question. This is from KCET batch. I don't remember the year, but this is also from KCET. So see the diagram, okay, and then pause the video if you want and answer the question immediately in the comment below. This is also easy question, not super difficult, only logic is required, mathematics is not required. Okay, pause the video, answer this question in the comment below, right? Now this is the end of the lecture today. I will be back with the part 3 of this chapter, and if you have any doubts, any questions, don't forget to ask me in the comment. Also you can see that these are the toppers from YouTube channel. They all studied from us in the YouTube, and they came and meet us. So if you want to do that, first of all you have to subscribe to our channel, secondly share this video with your friend, and obviously follow the lecture and follow like you want to be the topper, right? I will be back with the part 3 of this chapter. Then till then, bye.